Hello, this is the luckiest maths teacher in the world, and thank you so much for tuning into this video in which we will go through the concept of a field. So a field is a special type of ring, which means it's also a type of group. And the idea and what makes a field important is that the four basic operations, addition, subtraction, multiplication, and division, they work in a field the same way they do with our normal number system, our real number system. So let's go through a more formal definition of what a field is. So this is the formal definition of a field. So we're looking at a set of mathematical objects. So those mathematical objects form an abelian group under addition. The non-zero elements, so everything but the additive identity, form an abelian group under multiplication, and it also follows the distributive law. So note that 1 and 3, those conditions are needed for a ring. We also needed a few more conditions other than that for a ring. Remember, multiplication had to be associative, and under some definitions of a ring, you have to have the multiplicative identity and some you don't. So basically, a field is like a commutative ring, but the additional thing we have here is that each element has to have a multiplicative inverse. That was not required in a ring, but it is required in a field. So this will guarantee that division works like the same as it does with real numbers. So, just so we can understand this, so fields are a subset of integral domains. So what that means is that if something is a field, it will be an integral domain by construction. So the reason for that is because, remember, fields have to have multiplicative inverses. So if A is an element of the field, then that means its multiplicative inverse has to be a member of the field. So this means that any non-zero element of the field is a unit. So remember, we learned a few lessons ago that in our commutative rings, no element can be a zero divisor and a unit. So all the non-zero elements of a field, because they're units, cannot be zero divisors. So a field has no non-zero zero divisors, therefore it's an integral domain. And you can sort of perform division the way you can with normal numbers. So let's look at some examples of fields. So not every group we've studied is a field. So of course, if every field has to be an integral domain, that means that anything we've looked at that is not an integral domain is not a field. So we looked at things like the integers modulo 4, modulo 6, modulo 8, and we saw that all of these are not integral domains, therefore they're not fields. So sometimes the integers modulo n are fields, sometimes they're not. By the time you're watching this video, you've probably figured out which values for n make the integers modulo n a field, but I'm not going to tell you right here because I did leave it as an exercise. So the integers, for example, do not form a field, but the rational numbers do, and I want to leave you to think about why that is. So fields are very important because we can perform the four operations in them the same way we do for, say, real numbers. So fields are very important. We're going to learn about field extensions, and field extensions have a huge role to play in determining whether or not a polynomial is solvable, whether you can get the solution of a polynomial using just the four operations and also radicals like nth roots. So these are very important things in mathematics, so I really want you to get your head around them. Please ask if you have any questions. Otherwise, this has been the luckiest maths teacher in the world. Have a great day.